Alright, so in this video I'm going to introduce the concept of a partial derivative, and we're going to apply it to a function of two variables like this. So in the last video we discussed how a function of two variables, is essentially just a surface that is plotted on top of the xy plane. So basically the coordinate set is going to be a function of both x and y. So that's what a surface in three-dimensional space is defined as. So just to do a little bit of a recap of what the derivative is in two dimensions. So we have our xy plane, and if we draw a tangent line along a point, or instead we draw a line between any 2 points, so let's call this x and this x plus delta x, then we know that we can find the gradient of that line by having the following. So if we take delta y over delta x, that is essentially going to be the value of function y of x plus delta x minus y evaluated at x over the change in x, so that's going to be delta x. And if we take the limit now as delta x approaches 0, because you can imagine that these 2 points are going to come so close together that they're going to be collinear or almost collinear as delta x approaches 0, then what we have is the derivative, which is essentially just the gradient at a single point. So we're going to draw a tangent line at that single point, and this is defined as the limit as delta x goes to 0 of this particular function. So we're going to draw it like this. So that's what a derivative is in essence in the case of a function of a single variable f of x. So having defined that, what do you think is going to be the concept of a derivative in a two-dimensional function? Well, if we take, we're going to take two derivatives. We can take a derivative of z with respect to x, or a derivative of z with respect to y. And the main difference between them is that when we take the derivative of x, we're going to have to keep y constant, because we can only work with one variable at a time. And likewise, if we want to take the derivative of this function with respect to y, we need to treat x as a constant. And in doing so, we need to draw essentially two tangent lines at a point. So let's say we're interested in finding the gradient at this point here. So I'm going to call this point P. So let's find what the gradient is at that point. Well, if we direct our tangent in the x direction, so let's direct our tangent in the x direction, or rather the line between 2 points, as we did here, we're going to have some increment in x. So this is going to be x plus some increment in x, and this is just going to be the point x. So I'm just going to draw that here. Hopefully you can see that projection on this surface. Then obviously, what is going to be the derivative of this function with respect to x? Well, if we have this set over dx, we're going to have the following. We're going to have the function evaluated at the increment x plus delta x, comma y, because remember, y is not changing. This line is pointing in the x direction, so y remains unchanged, minus the original point, which is going to be xy, over our delta x change. And remember that, well, this should actually be delta, because we're talking about finitely small quantities. So if we take the limit now, obviously this is going to tend to the derivative. Now the only difference is that because we're taking partial derivatives, we need to use a different symbol, because remember that we need to basically make sure that we know that z is a function of two variables instead of one. So in order to do that, we use this symbol instead. So this is going to be equal to the limit as delta x goes to 0 of the function x plus delta x y minus f of x y over delta x. And now if we do the same thing, if we do the following, we know that if we take a tangent or a line that passes through 2 points along the y direction, then our derivative in that direction, or the gradient, is going to be equal to the following. So the partial derivative of z with respect to y is going to be equal to the limit as delta y goes to 0 on the function f of x y plus delta y, because now y is the variable that is changing, whereas x remains constant, minus f of x y, and this is going to be over delta y. So this is our definition of partial derivatives, and you can see immediately that we can extend this to higher dimensions, to n number of dimensions, because one of the variables is going to change at a time, whereas the other ones are going to remain constant or fixed. So the way this works is we're going to use the same rules of differentiation that we use in single variable calculus, but now we're going to treat the other variables in question as a constant for as long as we're differentiating with respect to the other one. So just to show you an example, let's have the function z equals to x squared plus x cubed y minus e to the xy. So this is just an example of a function that we may encounter. It's a function of two variables. So let's say we want to find the partial derivative of z with respect to x. So what we're going to do is we're going to differentiate every single variable or every single function of x with respect to x, and y is just going to be treated as a constant. So this one is going to become 2x. This one here is going to become 3x squared times y, because remember that y is not really x here, so we're just going to treat it as a constant. And here we're going to have, well, what's the derivative of this at the top? We know that we're differentiating with respect to x, so immediately that x is going to become a 1, and that y is just going to be a constant attached to it. So this should actually become y times e to the power of xy. And in a similar sense, if we wanted to differentiate this with respect to y, what we would get is the following. So partial derivative of z with respect to y is going to be equal to, well, x is treated as a constant in this case. So that means that this should go to 0 because the derivative of a constant is 0. And then here we're going to have y is going to go to 1 when we differentiate it. So this is just going to be x cubed, which is just a constant attached to it. And then we're going to have here, well, now we're differentiating with respect to y. So that means that our constant attached to it is going to be x. So this is going to be x times e to the power of minus xy. So immediately you see that that's the main difference between the two things. And you can see that there's a lot of things that we can do with this. So in general, the most common rule that you need to remember, so if we're differentiating a function that is uniquely a function of y, and we're differentiating that with respect to x, that's going to be 0 no matter what that function is. If that function doesn't contain any terms of x, then the partial derivative of that is going to be 0. So that's one of the fundamental things that we need to remember about this. And this is just the general concept behind it. So how does this actually translate when we have higher order derivatives? Well, that's quite an interesting concept, and I'm gonna show you just now. I'm gonna make some room here for this, and hopefully it makes sense that you have tangent lines running along each axis, x and y. And what do you think is going to result from that? At a single point, you're going to have a tangent line that's running along the y-axis and a tangent line running along the x-axis, and they're going to be perpendicular to each other. So they're going to be perpendicular to each other because these axes are perpendicular. And what you're going to end up with is, instead of a tangent line, you're going to end up with a tangent plane at that point. So you can imagine that if you have a surface like a sphere, right? Let's have a surface so similar to a sphere, or just a sphere. And if you find the partial derivatives at a point along that surface, then the partial derivatives with respect to the two variables are going to construct a tangent plane at that point. And that tangent plane is going to be defined by two things: the tangent the direction of the tangent line along the x direction and the direction of the tangent line along the y direction, and that's going to be a tangent plane, and it is going to span all the way to infinity in both directions. And same, if you draw the tangent plane at this point, then it's going to have a different gradient and a different orientation depending on what the function has. So instead of having this whole bunch of tangent lines, you have tangent planes covering the whole surface, and that's how we extend the concept of a derivative to higher dimensions. So now that we have defined those two things, let's now have a higher order partial derivative. So let's take another function. Let's have z equals to x squared y. Let's have it very simple. So if we find the partial derivative of this with respect to x, well, that's going to be 2xy. Partial derivative with respect to y is going to be equal to x squared. Now, what other derivatives can you think of? Well, what if we apply the differential operator with respect to x to this again? So let's have this. What do you think this is going to be? Well, this is just going to be the second derivative of z with respect to x. So what happens when we differentiate this again? We're going to get 2y. And how about this one? Let's apply the y differential operator to this once again. So this is the same as saying second derivative of z with respect to y. And that's just going to be 0 because this is just a function of x. So that's 0. Now you can have something called mixed derivatives, because remember, now we are working with two variables. So that means that we can apply this operator to that, and we can apply that operator to that. So if we do that, we're going to have the following. So partial derivative of x applied to the derivative with respect to y. This is going to be the same as writing this. And then what is this going to become equal to? Well, if we take the function that we had here, and now we differentiate it with respect to x, which is what we're doing, that's going to become 2x. And similarly, if we apply the same method to the following one, so let's apply the same method to this particular one. So partial derivative with respect to y to the partial derivative with respect to x is the same as writing second derivative, and this is a mixed derivative, equals to what? Well, we know that our first derivative with respect to x, that was 2xy. So now if we differentiate this with respect to y, we're just going to get 2x. And you notice something peculiar about these two things, and it is that they're actually the exact same thing. So what does that mean about the function? This essentially means that these two derivatives, these two mixed derivatives, are continuous, and it happens that if the second partial mixed derivatives of a function are continuous, then they're going to be equal, and that's quite a nice property of partial derivatives. Now obviously we can extend this concept further to higher derivatives. We can have something like the third derivative of a function. So I'm just going to erase this just to show you. So what happens with the third partial derivative? Well, now we can actually perform operations. We can either take differential with respect to x or y on 4 different ones. We can either apply to this or that one or that one or that one. So we're going to have 4 different third order partial differential equations, and the same is going to happen for them. If you want to have the fourth partial differential equation, that's the number of partial derivatives that you're going to have is going to keep increasing in the same manner. So these things tend to become quite complicated over time, but hopefully this gives you some intuition as to what partial derivatives are. And all you need to do is you apply the same rules of differentiation as you would with a single derivative, but now you basically treat the other variables as a constant as you're doing the partial differentiation with respect to a specific variable. And just to conclude this video, I'm going to show you what a different kind of notation is often used here. So let's have the function f of x, y. If we want to find the first derivative with respect to x, we often use this notation, but we can also use the notation as this. So a subscript of x means that we're taking the partial derivative of f with respect to x. Then in the same manner, we can have the following notation. This is just the shorthand notation, and it is equivalent to what we have when we have a function of a single variable and we have f prime as the shorthand notation for the derivative. So this is going to be the partial derivative of f with respect to y. And now if we want to have something like the second derivative with respect to x, what we're going to do is we're going to write this as f of x, now subscript of x, which is the same as saying f double x. And the same applies to y. So if we have second partial derivative with respect to y, that's going to be this function. Now differentiate with respect to y equals to f double y. And what happens with the mixed derivatives? How do we write the shorthand notation? Well, if you have this function, remember that now the operator with respect to x is acting on the derivative of f with respect to y. So this is the same as writing f of y now differentiated with respect to x. So the subscript x needs to go on the outside. So the order in which this appears here is going to be reversed here in the subscripts. So this is going to be f of yx. And similarly for the partial derivative, y times x, this is going to be the same as f of x now differentiated with y. So that's going to be fxy. And we will use the same thing with respect to functions that are functions of more variables, so 3 variables, 4 variables, and so on. So this is just the concept behind partial derivatives. And in the next video, we're going to discuss some of those differentiation rules applied to partial derivatives. So namely the chain rule, the product rule, the quotient rule, and so on.